Okay, so let's take a look at what the graph of the equation looks like. Graph the equation to see a visual of how far he can get. So I'm going to just write the equation that is in the problem so that we can have something to look at that we know that we're focusing on. Step 1, to graph an equation. Make an XY table and select a lot of small values for X. So this is one way to graph it, a line. You can just pick X and Y values. Let's see if I can get that to not capitalize. All right. I'm also going to show work on how to get Y in this column right here. So I'm just looking for small values that are easy to plug in. So I'm going to choose 0, 1, 2, and 3. If you're thinking how many are the minimum number of X's or how many X's do I need to put in, you need a minimum of 2. So I could have gone ahead and done just 0 and 1. However, if you want to graph accurately, it's a good idea to have 3 or 4 points to reinforce what your line should look like. So I'm going to go ahead and do 4 points here. And these are small values, they're easy to put in, so they will work. Step 2, plug in each X value into the equation and solve for Y. So I'm going to take my equation and plug 0 in for X and see what I get for an answer for Y. So Y equals 2.5 times 0 plus 1. Well, 2.5 times 0 is 0, but I still have to add that last 1. So 0 plus 1 is 1, so when X equals 0, my Y value is 1. In this situation, that means when 0 seconds pass, the Mr. Snickerdoodle has only gone 1 meter in front of his house, and that makes sense because he was standing there to begin with. All right, so then after 1 second, how far has he gone? So we're going to plug in X equals 1. So Y equals 2.5 times 1 plus 1. So 2.5 times 1 is 2.5 plus 1 is 3.5. So my answer is 3.5. That means when X equals 1, Y equals 3.5. It also means in this situation that in 1 second, Mr. Snickerdoodle will be 3.5 meters from his house. So that's what this point represents in this situation. So let's go ahead and plug in 2. So Y equals 2.5 times 2 plus 1. 2.5 times 2 is 5. Add 1, and my answer is 6. See if you can figure, say to yourself what this stands for, because the more times you say what the XY value actually stands for, the more you're going to be able to understand what this problem is talking about, and then the more you'll be able to interpret another word problem that or graph that you're able to do in the future. So the more times you write things down yourself, handwrite them, or verbalize things to yourself, the more you're going to get comfortable with the vocabulary of what's going on, and the more you can do that, the more you're going to actually be comfortable even with the ideas that the vocabulary stands for, and that's going to really help you when you're building ideas on top of these ones. All right, so if you figure it out, and you might want to pause the video before I say this. So if you did that, then this stands for when 2 seconds have passed, Mr. Snickerdoodle has moved 6 meters from his house. So now I'm going to plug in X equals 3 into the equation. Y equals 2.5 times 3 plus 1. 2.5 times 3 is 7.5. Add 1, and you get 8.5. So then try and say what this stands for, and you might want to pause the video. And then if you said that this stands for when 3 seconds pass, Mr. Snickerdoodle is 8.5 meters from his house. If you were able to verbalize that or handwrite it down, then you're doing good. You understand the material, and not only do you understand the material, but you've actually kind of made it more solid for your brain inside of your head because you've actually said it and actually written it. So you should be able to do a better job on this problem and on other problems that you kind of build your practice with. All right. So that was step 2 that I just did, plugging in each X value into the equation and solving for Y. So that's what I just did right here already. So step 3 is to graph the points and make a line. So I'm going to go ahead and graph these points and make a line with them. So my first coordinate point here in my table was 0, 1. So that means when my X value is 0, my Y value is 1. So X equals 0. So on this X axis, I'm going to go 0 over, which means don't move at all, sideways, and then my Y value is up. 1, so that's positive 1, so I'm going to go up 1. So that's my first coordinate point. My second one is 1, 3.5. So I'm going to move this over, starting from the origin. I'm going to move 1 over for the x and 3.5 up for the y value. And then the next point is 2, 6. So I'm going to, again, start at the origin, move over 2 on the x-axis sideways, horizontally, and then up 6. Okay. So there's my 2, 6 right there. Oh, it moved over. Let me fix that. All right. And then my last point is 3, 8.5 that I picked on my table. So I'm going to go start from the origin, move 3 over on my x-axis, and then go up to 8.5. All right. So if your point does not fit on the graph, you don't have to graph it, okay? So you just graph as many points as can fit on my grid. And all of my points fit, so that was fine. I graphed the points, and now I'm going to connect the dots with a line. And I'm going to see if I can cross all the points as well as I can. It looks like this point is a little bit off because at 1 it should be at 3.5, not at 2.5. So let me fix that point right there. So this point should have been at 3.5. So because at x is equals 1, y should be 3.5. So I'm going to move that over. And let's see if I graph. All right, so that's my graph. The x-axis represents time for seconds, and the y-axis represents distance in meters. So now let's take a look at this graph and see if I can do the same thing as I did with my xy table. So when x equals 0, my y value is 1. What does that mean? It means when no time passed, Mr. Snickerdoodle is 1 meter away from his house. This coordinate point is x equals 1 and y equals 3.5. That means in 1 second, if I go over here, Mr. Snickerdoodle has gone 3.5 meters from his house. If I skip to 3, how far is Mr. Snickerdoodle from his house in 3 seconds? Well, I go up here and it says 8.5. So I can see it in 3 seconds, that's how far Mr. Snickerdoodle is from his house. If I were to even go to 4 seconds, which I did not put in my table, so I don't have an exact answer here, and it doesn't even fit in my grid, but if I go up 4, then I should be able to get a good estimate, even though it's a little off my grid here. And it looks like it's about 11 meters. At 4, it's about 11 meters that he'll be from his house. So this is a good estimate or of where Mr. Snickerdoodle is in terms of distance from his house. Now, where can I see the rate of change in this graph? Well, it's the slope. The slope of this graph is going to say the rate of change, because if Mr. Snickerdoodle went 2.5 more for every 1 second, that means that this line is a certain slope here. If Mr. Snickerdoodle, imagine for a second that Mr. Snickerdoodle had gone 3 meters for every second. So let's insert a line. And let's make this line a different color, so that you can see the difference. So let's say he started in the same place, but he goes a little bit faster. So he starts at 1, but instead of only going 2.5 meters, let's say he goes 3 meters every second. That means in 1 second, he should be at 4, because he should go 3 more than 1, which is 4. And that means in 2 seconds, he should go 7, because he should have gone another 3, and 4 plus 3 is 7. So that should fall around here. And then in another 1 second, he should have gone 7 plus 3, which is 10. And that should be over here. If I can get my computer to show that. So let's see. So do you see how this brown line is ever so slightly more steep than the blue? So that brown line represents if Mr. Snickerdoodle had gone a rate of change of 3 meters per second instead of just 2.5. And you can see that it's slightly faster. So I'm going to also color that with a similar color, if I can get that there. All right. Now what if his rate of, I want to make this more dramatic. So let's pick a rate of change of, let's say 5 meters per second. So he still starts at the same place, around 1 meter from his house, but in 1 second now he goes 5 meters. So that means in 1 second, he's going to be 5 more. So he started at 1 meter, so now he's going to end up being 1 plus 5 is 6 meters from his house. And then that means in the 2 seconds, he's going to be 6 plus 5 is 11. So a little bit off the graph, but I can still make a good estimate. It should be 6 and then it should be 11. So in 1 second, he would be at 6, and then in 2 seconds, he would be at 6 plus 5 is 11. So this green line is the steepest of all. So we can see graphically that what a graph shows really well about a rate of change is how big it is. Just when you look at it, the steeper it is, the bigger the rate of change is. The less steep it is, the less steep it is. Okay, so that's why graphing can be very useful for studying rate of change. A line always has the same rate of change all throughout it, so that's why it's a good way to introduce the idea of rate of change to begin with. Now, I've been talking about slope a little bit, which you should have heard an awful lot in Algebra 1. So let's make a direct connection between rate of change and slope, because slope is just the graph of rate of change. That's all it is. So rate of change is a number. In a graph, that rate of change number is called a slope. So let's take a look now at how to study that. So show that for every unit on the graph, the y value goes up by 2.5 meters. So this is our original graph from Mr. Snickerdoodle. And I'm going to go ahead and write the equation down so that we can have it to look at again right here. So our equation for Mr. Snickerdoodle's distance was y equals 2.5x plus 1. And I'm gonna make that the color of the line-ish, at least close. Okay, x unit. For every x unit on the graph, which is time, the y value goes up by 2.5. So I'm just gonna go over 1 unit. So that's 1 x unit over there. And I'm gonna go see how much it goes up. So it goes up 1, 2, and then a little more, which ends up being 0.5. So 1, 2, it goes up 2.5. Oh, well, the y value stands for meters. So this shows that for every 1 second, this graph goes up by 2.5. I'm going to insert another and move it over here. So 1, 2, 2.5. So for every 1 unit, it goes up 2.5. So now, this should be the same rate of change as for all the other points on this graph. So, oh, it's not working here. Let's try. There we go. So that means that if I go 1 over from here and 2.5 over from here, it should be the exact same space, which it does seem to do. So if I go 1 over, it goes over a half unit here, then another full unit and another full unit. That's 2.5 units up. So that shows that for every 1 unit, it's going up 2.5 again. Let's try it again and see if it works again. Well, if I do that here, it also seems to work. So if I go 1 unit over on time, it's going up 1, 2, and then another half unit. So it's going up by 2.5 meters for every 1 second. Even if I were to continue this on and on, it should follow up. So if I did this again for the next one, which we did not find in our table, but it does match our graph. If I move 1 unit over, then it goes up a half a unit plus 1, 2 full units. So that's 2.5 units up. And then if I go even backwards, it should also follow anywhere else, anywhere on the graph. So if I even skipped a few and went down here, it should fit, and it does, because if I go 1 unit over, the graph goes 1, 2, 2.5 units over. So this is the next point up here. So this shows, if you need to show that something goes up by 2.5, this is how you would do it, and you would just mark up the number 1 down here and the number 2.5 on the side of the triangle. Okay, so let me then move on to another question. Well, the slope is a vocabulary word that stands for the rate of change in a linear graph. We talked about that just a moment ago. So that means that the slope of this graph should be the same as the rate of change in the equation. And the slope is just a vocabulary word that stands for rate of change in a linear graph. That's what slope means. The variable that we use when it stands for slope in this formula case, it stands for the value of the slope. So the formula for slope, if you, which you should know because you should have already learned this, is change of y over change of x. That triangle is the math symbol for change. So this is equal to change of y over change of x. That's what the triangle symbol means, is change. The formula to find change is you take the any two coordinate points you know. So for example, if you know that x1 and y1 are coordinates and x2 and y2 are coordinates of, on the same line, then you can just use this formula to find out how much y changed. So subtract the y values to find out how much they've changed on the top and divide by how much the x's have changed on the bottom. Which you'll notice is pretty much what we did all the way back here. We saw how much the x values changed, which was just always 1. I just made it really easy for the x values. I made it only change by 1. So this change from 1 to 2 was 1. And then the change from this height, which was 3.5 to 6, is 6 minus 3.5 is, if you do 6 minus 3.5, you'll get 2.5, which was this height. So that's what we were always doing anyways when we made those little dotted triangles. So we're going to use this formula to show that the slope is always 2.5 meters per second, no matter which 2 points you use. We did that a little bit with the graph, and now we're going to do it with the algebra, okay? Now notice I called this x1, and I wasn't able to make the sub very quickly, but I'll do that just so that no one gets confused, because that should be x sub 1 and y sub 1. Same thing for this. That's another coordinate, which we're just going to label as x2 and y2 because it's another x and another y, not the same as the first x and y. All right, so if I go back to my table of points here, all the way back here, I'm just going to pick 2 of the points. And I want to show that that formula is true no matter what. So I'm going to choose 1, 3.5, and 3, 8.5. Those are the 2 points I'm going to use, 1, 3.5, and 3, 8.5. Could I have used another set of points? Absolutely. You can choose any 2 points in this table. So I'm going to just choose 1, 3.5, and 3, 8.5, but you can choose another pair and see. So I'm going to go back to here, and I'm going to choose, my first example is going to be 1, 3.5, and 3, 8.5. So to use the formula, this is my x1. I'm going to just use this again. This is my x1, my y1, and then the second point is going to be my x2, y2. How do I know which one is x1, y1, and which one's x2, y2? Well, it doesn't matter. So you just pick one point, label it x1, y1, and then the other point has to be x2, y2. So it doesn't matter which point is which, as long as you just pick and then you stick with whatever you chose. All right, so my formula is y2 minus y1 on the top. So I'm going to take my y2, which is 8.5, and I'm going to subtract the other y, which is 3.5. So 8.5 minus 3.5 is the top number. And then I'm going to put that, let's just underline it, over my x is subtracted. So my bottom of my formula is x2 minus x1. Well, my x2 is 3, then I'm going to subtract the other x, which is 1. So I will go ahead and put 3 minus 1 for the bottom number. That's going to get me, it's not anymore, 8.5 minus 3.5 is 5, and then 3 minus 1 on the bottom of that fraction is going to be 2. So 5 divided by 2 is going to get me 2.5. So my slope is 2.5, which they said show that the slope is always 2.5 meters per second. So the slope is 2.5. And then because the problem is in meters per second, it's going to be meters per second. Well, this said no matter which 2 points you use. So I only chose one set of points. Let's do another set of points to show that it didn't matter whether I chose this coordinate point or another one. So we're going to now choose another set. So again, you can choose whichever coordinates you want. I'm going to choose 3, 8.5, and 0, 1. Okay, 3, 8.5, and 0, 1. Doesn't matter which ones you choose, so I'm going to choose those two. So 3, 8.5, and 0, 1. Notice I'm flip-flopping the order of the points this time to show you it doesn't matter. So I'm going to label the first points x1, y1, And I'm going to label the second points x2, y2. So this is x1, this is y1. This is x2, this is y2. And now I'm going to use my formula. So the formula is subtract the y's on the top, so y2 minus y1. So my y2 is 1, my y1 is 8.5. So that's going to be 1 minus 8.5. I'm going to put a fraction bar. And below that, the formula is x2 minus x1. So I'm going to take my x2, which is 0, and subtract the other x, which is 3. So do that. 0 minus 3. So 1 minus 8.5. So you can do that on a calculator or figure it out, and it's going to be negative 7.5 on the top. And then put a fraction bar underneath, and 0 minus 3 is going to be negative 3. If you do that, negative 7.5 divided by negative 3 is going to be a positive 2.5. So the slope is going to be 2.5 again. And because of this problem, it's 2.5 meters per second, but the slope itself is just 2.5. So if I do this with any 2 points on that line, it will always end up being 2.5.